GPS, INS coupling system. The INS and GPS are complementary. The INS detects the navigation information, position, velocity, and attitude, of moving bodies using an accelerometer and gyroscope. The precision and cost of an INS are exponentially proportional and its error increases with time. However, it is more stable than other systems because it can obtain information about three axes, X, Y, and Z, and has no communication problems. It has the advantage of not being affected by the external environment, and providing highly accurate and continuous navigation data for short voyage durations. The GPS is a system that determines the position and velocity of moving bodies by measuring the pseudo-range to moving bodies from at least 4 of the 24 satellites orbiting the Earth. The GPS is relatively low-priced, does not accumulate errors with time, and the error range is fixed. However, its disadvantage is that the performance drops if there is severe jamming, or the number of visible satellites is less than 4. Furthermore, visibility and communication may become restricted. If you design a navigation system using only one method, high costs are required to obtain the desired performance. However, high-performing sensors can be obtained at low cost if you consider complementary performance. Thus, the navigation system of ground equipment and the orbiter of a space probe are designed to complement each other. We can design navigation systems more effectively by using the INS and performing periodic calibrations with GPS. Furthermore, this can make the overall navigation system more robust than if using only one method. Current research is attempting to integrate these two systems, using integration methods that can be largely divided into tight and loose INS, GPS integration systems. One characteristic of these integration systems is that the performance can be enhanced by improving the tracking performance of the code and carrier tracking loops of the GPS receiver. The structure of the tightly coupled INS, GPS integration system is shown in Figure 5. Data measured from the GPS receiver, pseudo-range rate, and the INS data, position, velocity, attitude, include many errors. The INS and GPS do not perform separate filtering, but these errors are estimated by one common filter. The loosely coupled INS, GPS integration system is shown in Figure 6. In this system, INS and GPS perform measuring and filtering separately. Tightly coupled INS, GPS integration systems. Loosely coupled INS, GPS integration systems. The loosely coupled system can be smaller and faster than the tightly coupled system. However, noises also become amplified. The performance of loosely coupled and tightly coupled integration is the same if the GPS availability is good throughout the test run. When GPS availability is poor, as in an urban canyon, tightly coupled integration performs better than loosely coupled integration. The positional accuracy is best when both code and Doppler measurements are used, and is worst when only Doppler measurements are used. The velocity accuracy is also best when both code and Doppler measurements are used, and worst when code only measurement is used.